Welcome to the class of medical physics. In previous lecture, we have discussed that we have two types of electricity. One is static and the other one is current electricity. So today's lecture is based on the current electricity. The first topic for current electricity is electrical conduction. Electrical conduction is the movement of electrically charged particle through a transmission medium. This movement can form an electric current in response to an electric field. The underlying mechanism for this movement depends upon the material. Electrical conduction occurs due to the presence of free electrons present inside the conductor that contributes in the conduction of electricity, or the movement of those free electrons cause the current through a proper transmission medium. That is your path of transmission of current. The electric current is produced in response to an electric field. You have dielectric charges, and in the presence of those electric charges, you have certain electric field. And when free electrons flow in from that electric field, they produce electric current. But the underlying mechanism for this movement also very much depends upon the material, whether the material is good conductor, a moderate conductor, or a bad conductor or insulator. That varies. The definition of current, or the nature of current will be is very much more dependent on the material. Next is valence electron. Electrons in the last shell or energy level of an atom are called valence electron. In last class, we have discussed the energy orbitals. So in every energy shell, you have certain number of electrons is specified by a formula we have discussed as 2n square. So each electron has a certain energy level and a limited number of electrons to be occupied. But the very last electron of any atom also contain a particular number of electron according to their atomic number, and the number of electrons present in the last shells are called valence electron. As you can see in the figure, here is a material in which the number of electrons in the last orbital are 6, so means they are 6 valence electron. We have discussed earlier that in any neutral atom, the number of electrons present in the outermost shell are stable by default. It doesn't matter whether the last orbital is complete or not, but by default, the number of electrons present in the outermost shell are neutral by nature, by default. But as you can see in this atom, the number of electrons are 6. This is by default naturally neutral atom. But as soon as when you pick out one electron out of this atom, what will happen? There will be create a void, an empty space at the place of this electron when it will jump out of the last valence shell, the last energy orbital. There will be a vacant space at this position. So, and that this event will make this atom, the naturally neutral atom, as a positively charged particle, positively charged atom, because there is a valence, there is a hole present. Now, there is a hole present in the atom, and the in neutral state, it should contain 6 electron in its outermost shell, whereas now it has 5 electrons and there is a hole in its outermost shell. So this property is making it to a positively charged element, positively charged atom. Likewise, if we reverse the case and due to any certain event, if any external electron from nowhere will come and adjust into this outermost shell, or there is an excess amount of electron, although the capacity of this orbital is 18, but by default this element, this atom sustained 6 electrons. Now it is having the seventh one as extra electron, and the atom is holding up that electron because the outermost shell has capacity to hold 18 electron in its outermost shell, because this is the third one, the third shell, so it can hold up more electrons. And when an outermost electron come and stick to that orbital, this property, this event will make this atom a negatively charged particle. So last energy shell, level 3, count of electrons in the energy level, there are 6 valence electron. But if you increase the number of electron or if you decrease the number of electron, will change their polarity and will make the atom as positively charged element atom or negatively charged particle, whatever. So I think this is pretty much clear now. Okay. Electrons in an atom can have only certain well-defined energies. This point is also being very much discussed in previous lecture, that you can see you have first energy orbital in which we have 1 and 2 electrons. The energy level of these 2 electrons will be different to the electrons present in other energy levels. And the least amount of energy will present in electron present in K shell, K orbital, and whereas pink shell, this pink one that is L, will, and the electrons in this present in this shell will have more energy than K orbital electron, and likewise the blue one, the valence shell electrons, will have more energy than the previous ones. So the electrons are said to occupy particular energy level. In a typical atom with many electrons, the lower energy levels are filled, each with the number of electrons allowed. A quantum mechanical rule known as Pauli exclusion principle. Depending on the element, the highest energy level to have electrons may or may not be completely full. Depending upon the element, it depends upon or it varies from element to element, the highest energy level, that how much electrons are present in their highest energy level, and both are the possibilities that their valence shell could be completely filled or could not be completely filled. In either case, whatever the number of electrons are naturally present in the valence electron, they are naturally neutral atoms until and unless they exceed by that number of electron or they deficient by that number of electron that are naturally present into their valence shell. So other than that, whether the valence shells are completely filled or not, it doesn't matter. The both cases are naturally occurring. So here are example of inert gases. What are inert gases? Inert gases are the element in which their outermost shell, the valence shell, whatever the number of shell is that, they are completely filled. And if the outermost shell of any element is completely filled, they are known as inert element and particularly inert gases. We have the last column in our periodic table for inert gases, and those are also known as noble gases. Their names are helium, neon, argon, krypton, xenon, and radon. In helium, it contains only one orbital, and the number of electron, the maximum number of electron could be present in K shell is 2. So In helium atom, two electrons are present at all the time. So this makes the property, this makes it an atom which we call the inert gases. The next is neon. Neon has two valence orbital or two energy orbitals in its structure, and the second energy orbital has the capacity to bear total number of 8 electrons, and neon has the total number of electrons present in its outermost shell, which makes it again inert element. So what are the basic or you can say specified properties of inert gases that we are supposed to discuss as separate topic? Is that the elements of atom of which all shells are completely filled are called inert gases or noble gases or rare gases. In modern periodic table, they are placed in zero group. Under ordinary condition, these elements are chemically inert due to their stable electronic configuration. Electronic configuration is very much stable that their outermost shell are completely filled. That is why the main property or the you can say identity of these inert gases is that they do not react with other elements so easily or not at all, because they are very much stable atoms that they don't need to give off their outer any of outermost electron, because their bondings are very much strong enough with their nucleus. Neither they can adapt or intake any electron from any other atom, because they don't have capacity to take more of them. If you consider the helium, it has only K shell, and K shell has capacity to pair only two electrons, and helium itself has two electrons in neutral state. So it does not need to carry on or to adopt any further electron. It has no vacant space, it has no capacity anymore. Same goes with the neon. Neon, it has two energy levels, and the outermost level have capacity to bear 8 electrons, which is completely filled. So inert gases do not react with other elements. They are all gaseous elements, and their names are so and so. Okay, so here are a few practice questions in assignment. Like you need to write down 5 uses and application of inert gases in daily life, and 5 applications of inert gases in clinical practice and medical imaging. You need to properly find out or go through the research papers, latest research papers. I insist to go through them and to find out the applications of inert gases in medical imaging, in inert clinical practice, how we are consuming them and how they are helpful. So next is semiconductors. Okay, we have discussed in previous lecture that we about the conductors and insulators, but we have something in between them that are semiconductors. And semiconductors are very much useful in especially electronic engineering, electronic instruments and equipments making. Why semiconductors are very much useful, or why do we even using them? The main property is that their properties lie in between the conductors and insulators, because they are semiconductors. So materials are classified as conductors, insulators, or semiconductors according to their electrical conductivity. We have classified them. Again, I'm repeating, we are talking about electrical conduction, not thermal conduction in this case. So semiconductors are somewhat lies in between the conductors and insulators. Semiconductors are material which have a conductivity lies between the conductors, generally metals, and non-conductors or insulators. Semiconductors can be pure elements such as silicon and germanium, or compounds such as gallium arsenide or cadmium selenide. Okay. Within nature, we do have semiconductors, and we go for the manufacturing of semiconductors as well. Like we have a compound such as gallium arsenide and cadmium selenide. Okay. Um, we also enhance the property, or I could say, we control the conductivity of semiconductors through a process called doping. What is doping? Doping is a process in which very much least amount or small amount of impurities are added to semiconductors, causing large changes in the conductivity of the material. So, by the variation of or adding up the impurities, we control the conductivity of semiconductors. That how much conduction we do need to conduct, we do need for the conduction of electricity. So, here are the examples of semiconductors. Sorry, application of semiconductors, which the devices which are made up of semiconductors. These all are electronic devices. The one is op-amp, resistors, capacitors, IC, transistor, and diodes. All are using semiconductor materials. Why don't we use conducting materials directly into for those electronic devices? The reason is that electrical conduction is very much high. um that if you use conducting material directly into that, like your silver, copper, brass, in these elements for these devices, small devices, so there are chances to burning up of those devices due to high or immense conduction through conducting materials. That is why we use, or it is necessary to use, the semiconductor for these devices, in which the amount of voltage applied is very much low. Okay, now here comes a term, impurity. What is mean by impurity? Impurity are the addition of positively charged elements or the negatively charged particles to increase the polarity for electrical conductivity. So impurities are added in the process of doping, and that could be addition of electrically charged particle, both positive and negative, that further enhance or control the conduction of electricity. Okay, now we have few definitions. The number one is current. What is current? Current is any flow of liquid. Of course, solid never flow. So flow of liquid or flow of gases are known as current. You have water currents, you have air currents. So the part of a fluid body such as air or water moving continuously in a certain direction sustain certain amount of current. They have certain amount of um, you can say the measurement of how much that fluid is flowing with how much capability capacity would be regarded as your current. But here in electricity and magnetism, we do need to talk about electric current only. That we denote through I, capital I, or we can also use a small I for that. An electric current is a flow of electrons, flow of electric charges like water flow through water hose, or an electric current is a stream of charged particles such as electrons or ions moving through an electrical conductor or a space. It is measured as the net rate of flow of electric charge through a surface or into a controlled volume. The unit of electric current is ampere. How much charge is flowing through a surface into a controlled volume? Through this measurement, you can calculate the current. In this diagram, you can see there is a complete circuit in which we have a supply battery and a load which is consuming the current. When you supply voltage, the free electrons present into the path of the circuit will start moving, will start flowing because of this supplied voltage that gives off the pressure to the free electrons to start moving. You will see the bulb will glow and because of the complete path and the moving of electron. So the flow of electron generates electricity or electric current. The unit in which we measure the electric current is ampere. Something more about electric current. Okay. In 1752, prior to electricity being identified with electrons, Ben Franklin chose a convention regarding the direction of current flow. He assumed that the positive charge carriers flow from positive to negative terminals, which was incorrect basically, and that was uh, termed as incorrect after the discovery of electron, because it was known that the current flow occur is a result of flow of electrons and not the flow of positive charge particles. Ben Franklin assumed that the current is a flow of positive charge carriers, which was wrong. Neither positive charge carriers do not flow when and produce current. The flow occurs due to the flow of free electrons present into the conductor, but and not the positive charges. But convention was not discarded and both the currents were defined. Hence, electric current is the flow of electron, the negative charges in a circuit, and it is directed from the negative terminal to the positive terminal. The direction the current electric current follow is from negative terminal of supply to the positive terminal, as this says that the direction or the current is happening because of the flow of electrons. So electrons emerge from negative terminal and gets attracted towards the positive terminal, and in that whole path whatever the load you attached will consume that energy of flow of electrons. So that was the electric current, whereas the conventional current, on the other hand, would said that the flow of positive charges produce the current and it is directed from positive terminal of the battery to the negative terminal, which was wrong. But you will see in everywhere we do follow the direction of conventional current through arrowheads because it has been using since the start and does not change. So we will experience most of the time the arrowheads are showing the direction of conventional current rather than the direction of electric current. Whatever the direction you will experience, both are correct, but the common one is the direction of conventional current to be followed. Okay, so these two diagrams are showing you the what I am talking about, the directions from positive terminal through the load till towards the negative terminal is the direction of conventional current, whereas in electron current the convention is right, that is the flow of electron from negative terminals flow throughout the circuit and gets attracted by the positive terminal of the battery or supply. Meanwhile, this flow is used as energy to run your any of the component attached within it. Like you, if you attach the electric bulb, your ceiling fan, or whatsoever, or any of the LED or anything, the flow of electrons will help out to generate the electricity. As you all know that in nature we have two laws. The one is let me type it for you. We have two laws of nature. One is law of conservation of energy, and the other one is law of conservation of mass. I hope most of you people are very much familiar of these two laws because they are the basic one. Law of, law of conservation of energy says that energy can neither be created nor be destroyed, but it can be transformed from one form to another. And same goes with law of conservation of mass. States that the mass can neither be created nor be destroyed, but it can be transformed from one form to another. So, according to law of conservation of energy, if I relate it to the topic, how do we produce electricity? Through wind energy, through water energy. The flow of water generates energy through turbines and all that. Likewise, the flow of electron produce or converts the chemical energy into the other form of energy of your appliance. For example, in case of LED or glowing, the chemical energy will convert into electrical energy, and electrical energy will convert into the light energy. And light energy will further convert into heat energy, which absorbed by your surrounding. So there are transformation of energies. I repeat, this chemical energy of your battery will convert through the flow of electrons into electrical energy. This electrical energy, if you consider this load as a glowing bulb, so electrical energy will convert into chemical energy, the third form of energy. And this light energy will go further into your surrounding and absorbed by it or remain into there as heat energy. Heat energy. So you saw the transformations of energy from one form to another. So in this very small little example, you have four conversions of energies at the same time: the chemical to electrical, electrical to light, and light to heat energy. So here are multiple example, huge number of example in your daily lives of the conversion of energies, which you don't even noticed in your daily life. Okay. So that was about the direction of flow of electrons within a circuit. However, the arrow in circuit I am sorry if there are fluctuations in the recordings in between. So I just need to repeat few words. It is important to realize the difference between the conventional current flow and electron flow in no way affects any real world behavior or computational results. Whatever the convention you are practicing or you are using for your circuit diagrams to show the flow of current, it doesn't get affect the original internal mechanism of current flow. So the both are same. That is why. In general, analyzing an electrical circuit yields results that are independent of assumed direction of current to be flow. Conventional current flow is a standard that most of all the world follows. That's it. Ammeter is a device that is used to measure the current. How do we use ammeter and how do we arrange that ammeter in the circuit will be discussed in near future. Next is voltage. Voltage is a pressure from an electrical circuit power source that pushes charged electrons current through a conducting loop, enabling them to do work such as illuminating a light. As you can see in this diagram, this is a very good representation. You have a battery and which is a pressure applying source, and on which they are applying the pressure on the free electrons. They are basically stimulating the free electrons to start moving the initial push. So the battery is a very useful element to initiate or stimulate the flow of current. It applies pressure to the free electrons present in the whole circuitry of conducting material. And after that initial push, the electrons start flowing and keep on flowing until unless you break the circuit. So here is also internal representation of voltage. You have a battery and you have accumulation of charges. Battery is nothing but a storage material. Yes, like we have discussed in capacitor. So voltage is being applied by a battery, any external source, which is a storage medium, and this, after getting a complete circuit, it starts or initiate the process of flow of electrons and supports throughout. SI System International Base Unit for measuring this pressure, this electrical pressure, is voltage. Next is the difference between electromotive force and potential difference. What is electromotive force? That is also represented or written as EMF, and potential difference. These are both in the same thing. The both are voltages. But what is the difference between them? Is there is a very little difference between them actually. The voltage of a power source such as batteries drops when they are connected with a circuit having load resistance. This is obvious when you apply voltage and a load, any consuming element is attached with the circuit, you will lose lose the battery with after a certain amount of time, because that voltage is being consumed by the load attached within the circuit. That is why. So get back to the potential difference. Potential difference is that particular amount of voltage which is being used by any load. So the voltage drop occur due to that load is known as the potential difference. Here it is written the voltage drop is due to internal resistance inside the batteries as well. Okay. Batteries also have their internal resistance. So voltage drop also occur at batteries as well. This reduced voltage is known as potential difference. The reduction in voltage at any point, at any level, or at any element, what how much the voltage is being consumed by that element or that material load, will be known as your voltage drop, and it depends on the connected load, while the EMF is unloaded voltage of the battery or power supply. Voltage potential difference is the difference in any voltages before and after the load, whereas electromotive force is the overall voltage of the circuit through which the circuit is running. The potential difference is always less than the EMF. Of course, EMF is the voltage of the whole circuitry, and the EMF is maximum voltage the battery can supply. If you are using a battery of 10 voltage, for instance, in any circuit, so the EMF of that circuit is 10 volts, the voltage applied by the battery. If you attach a battery of, let's say, 20 volts or 50 volts, the EMF of that circuit will be 20 volts or 50 volts, likewise. Whereas the potential difference will be um known or will be calculated as how much loads are applied into that circuit and how much voltage is consuming by those loads will be calculated as voltage drop. For instance, if I like to draw a circuit for you, there is a battery. The symbol of battery is like this. You do have a load. Apologies with my drawing. And next is you have any other load, that could be anything. I'm just drawing a resistance over here because load are also resistances. So this is the complete passage or a complete circuitry. So how much voltage is coming at that point and how much will remain at this level? For example, 5 volt is coming to that point, whereas 2 volts will remain after passing through this LED or bulb, whatever. So the difference of 5 minus 2 is 3. It means the voltage drop occurs at this point of this LED is of 3 volts, whereas the EMF of that circuit was 10 volts. The battery attached to that circuit was of 10 voltage. Next, this 2 volt is coming to this further load applied, and you measure that the voltage remains after passing through this resistance is, let's say, 1.5 volts. So how much voltage was consumed by this load resistance was your zero point 0.5 volts. So it depends upon the load, how much voltage drop is occurring at any each level, each particular level is known as your voltage drop, and the voltage drop is also known as your potential difference, that is PD. I repeat, the unit for all these voltages are same, that is volts. The only um, condition to measure the voltage drop or EMF is that this your circuit should be complete. If the circuit will be break at any point, there won't be any current flow and you will not be able to calculate the EMF or either the voltage. So I hope this is quite clear to everyone. Okay. So EMF is the maximum potential difference between 2 points of the battery when no current is flowing through the source in case of open circuit, whereas potential difference is the difference in amount of energy that charge carriers have between 2 points in a circuit. Here is the example. You have an EMF, the flow of current, and a load resistance. You will have different um, voltages at point B and A, and the difference of the uh, difference in voltage will be known as your potential difference. However, if you calculate the same difference in potential at the point of subsource, you will get the maximum difference, maximum potential difference, and that maximum potential difference is known as the EMF. Voltmeter is a device to measure the voltage, EMF, or the potential difference. Next is resistance. Resistance is the measure of opposition of current to flow in an electrical circuit. It is measured in ohms, symbolized by Greek letter omega. Ohms are named after George Simon Ohm, a German physicist who studied the relationship between voltage, current, and resistance. He is credited for formulating Ohm law, the famous law of in the world is Ohm's law in the world of electricity and electronics. Here is the example of water hose in which we have two pipes of different diameter. As you can see, the water will flow easily or more quickly through this pipe A, whereas it will go with more pressure but with least amount as compared to the first one due to its very much low diameter. This is what where resistance incorporate the resistance in flowing of water. Amperage is nothing but the flow of current, the measure of flow of current. The term comes from the ampere. So resistance measurements are easily important to indicate the condition of a circuit. Resistance, I repeat, is a very much important element, and you will um, experience it again and again. The higher the resistance, the lower the current flow, as there was more resistance in water flowing, so the flow of water was less than the first one. Highly increase in resistance could also damage conductors through burning or corrosion. The more will be the resistance, the more will be the metal heat up, and the more are the chances of burning up or corrosion of that material. All conductors give off some degree of heat, so overheating is an issue often associated with resistance. The lower the resistance, the higher the current flow. But I want to give you a very important point that resistance has both positive and negative effects in electrical components. In electronic components, somewhere at some points, we do need to um, we do need to incorporate the effect of resistance, which are very much necessary for the circuit. And at some points, we also do need to minimize the effect of resistance which are present itself within the circuit. So it has both advantages and disadvantages. Many components such as heating elements and resistors have a fixed resistance value. These values are often printed on components, nameplates in manuals for references. Resistance may sound negative, but in electricity it is beneficial as well. Here is an example of bread toaster, which I'm using it to show the useful application of resistance. What happened, or what is the mechanism of bread toaster? Let me explain the example. Current must struggle to flow through the small coils of toaster enough to generate heat that browns your bread. Old style incandescent bulbs, light bulbs also use um, forceful current flow through the filament of thin wires or thin filament so that the light generates. Both things happen when you use fine wirings. When you use fine wirings and start allowing the current to flow through them, the fine wirings, the wirings with very much least amount of diameter, will experience huge resistance in the flow of electron in the and the huge resistance in the passage of flow of electron. So that resistance, or that friction in flow of electron will ended up as will generate heat. That heat is used as basically for a useful purpose to brown your bread. Likewise, where the resistance encounter in the flow of electron, the passage of flow of electron, two things happen. Number one, it heat ups your surrounding, it heat ups the conductor, as well as it generates light. So the light phenomena is used in old incandescent bulbs, where if you have seen those bulbs of 60-watt power, will have very very fine filaments. So when you start flowing electrons through those fine wirings, they experience huge resistance, and due to that, and it eliminate light, which we use as a source of light. So heating the useful purpose of resistance we are using in terms of heat and in terms of light both. We do have negative effects of resistance as well in many of the circuits, because we want our circuitry to be safe from burning. So for that purpose we use heat sinks, and many other processes are there. But this is the end of today's class, so I hope things are very much clear at your end. That's it. Thank you for having us.